Good morning, students. For the last slide, we had seen the dual nature of radiation. Now we are going to see the part 2, that is matter waves. Topics to be covered in this part are introduction, de Broglie wave, de Broglie wavelength and de Broglie wavelength of an electron, Davison and GERMER experiment, electron microscope, X-rays, production and properties of X-rays, X-ray spectra and its types, and applications of X-rays. The first is introduction. So far, we learned that the characteristics of particles and waves are different. Here, a wave is specified by its frequency, wavelength, wave velocity, amplitude, and intensity. It spreads out and occupies a relatively large region of space. And a particle specified by its mass, velocity, momentum, and energy occupies a definite position in space and it is very small in size. In quantum theory, the dual character for radiation, that is, radiation behaves as a wave at times and as a particle at other times. And the first topic is de Broglie wave. According to de Broglie, a moving particle can be associated with a wave. That is, a wave can guide the motion of the particle. The waves associated with the moving material particles are known as de Broglie waves or matter waves. According to de Broglie hypothesis, all matter particles like electrons, protons, neutrons in motion are associated with waves. These waves are called de Broglie waves or matter waves. And the next one, we are going to find the de Broglie wavelength formula. The momentum of photon of frequency nu is given by P equal to h nu by c. We know that nu by c is nothing but 1 by lambda. So the formula P equal to h by lambda. The wavelength of photon in terms of its momentum is lambda equal to h by p. For a particle of mass traveling with a speed, the wavelength is given by lambda equal to h by mv because momentum equal to mv. Then the relation is lambda equal to h by p. This wavelength of the matter waves is known as de Broglie wavelength. And the thing is, this equation relates the wave character and the particle character through Planck constant, that is h. The next topic is de Broglie wavelength of electrons. An electron of mass m is accelerated through a potential difference of volt. The kinetic energy acquired by the electron is given by half mv square equal to electron volt eV. Therefore, the speed of the electron is v equal to root of 2 eV by m. Hence, the de Broglie wavelength of the electron is lambda equal to h by mv. Here we are substituting the v value here, then the equation becomes lambda equal to h by root of 2 eMv. Now substituting the known values of the above equation, that is lambda equal to 6.626 into 10 power minus 34 by root of 2v into 1.6 into 10 power minus 19 into 9.1 into 10 power minus 31. By multiplying and dividing the equation, we can get that lambda equal to 12.27 into 10 power minus 10 by root V meter. In terms of Armstrong, the equation becomes lambda equal to 12.27 by root V Armstrong. For example, if you are applying the potential difference of 100 volt, then its de Broglie wavelength is 1.227 Armstrong. Since the kinetic energy of electron, that is K equal to electron volt EV, then the de Broglie wavelength associated with electron can also be written as lambda equal to h by root of 2mk. The next most important topic is Davison-Germer experiment. The Davison-Germer experiment was a physics experiment conducted by American physicists Clinton Davison and Lester Germer in 1927, which confirmed the de Broglie hypothesis. This hypothesis, advanced by Louis de Broglie in 1924, says that particles of matter such as electrons have wave-like properties. This experiment not only played a major role in verifying the de Broglie hypothesis and demonstrated the wave-particle duality. From the figure, F is nothing but filament, C is a cathode, A is a anode, and V is a voltage, that is battery. Initially, a beam of electrons emitted by the electron gun is made to fall on nickel crystal cut along cubical axis at a particular angle. The scattered beam of electron is received by the detector, which can be rotated at any angle. The energy of the incident beam of electrons can be varied by changing the applied voltage to the electron gun. The intensity of scattered beam of electrons is found to be maximum when the angle of scattering is 50 degree and the accelerating potential is 54 volt. For nickel crystal, the lattice spacing value is D equal to 0.91 Armstrong. The electron diffraction is similar to X-ray diffraction, which means from Bragg's equation we know the formula 2d sin theta equal to n lambda, which gives the value is lambda equal to 1.65 Armstrong. The wavelength can also be calculated from de Broglie relation, that is V equal to 54 volt. Then the equation is lambda equal to 12.27 by root of V Armstrong. By substituting the V value is 54 volt, then the equation becomes lambda equal to 12.27 by root of 54, that is equal to 1.67 Armstrong. This value agrees well with the experimentally observed wavelength of 1.65 Armstrong. Thus, this experiment directly verifies the de Broglie hypothesis. The next interesting topic is electron microscope. What is electron microscope? The electron microscope is a type of microscope that uses a beam of electrons to create an image of the specimen. It is capable of much higher magnification and has a greater resolving power than a light microscope, allowing it to see much smaller objects in finer. The principle of electron microscope is wave nature of moving electron. Why we use electrons instead of light? The reason is, in 1920s, it was discovered that accelerated electrons behave in vacuum just like light. They travel in straight lines and have a wavelength which is about 1 lakh times smaller than that of light. Furthermore, it was found that electric and magnetic fields have the same effect on electrons as glass lenses and mirrors have on visible light. Now we will see the parts of electron microscope. The first is electron gun. Electron gun is nothing but it consists of a tungsten filament or a cathode that emits electrons on receiving high voltage electric current. The second part is ray tube. It is a high vacuum metal tube. It is of 2-meter height through which electrons travel. The third one is condense lens. What is condense lens? It is an electromagnetic coil which focuses the electron beam in the plane of the specimen. The fourth part is projectile lens. It is also an electromagnetic coil which further magnifies the first image formed by the objective lens and produces the final image. The last part is photographic film. Since unaided human eye cannot observe electrons, therefore a fluorescent screen is used for viewing the final image of the specimen. Next, how the electron microscope works. This electron microscope is similar to that of an optical microscope, except than an electron microscope. Focusing of electron beam is done by the electrostatic or magnetic lenses. The electron beam passing across a suitably arranged either electric or magnetic field undergoes divergence or convergence. The electrons are emitted from the source or accelerated by high potentials. The beam is made parallel by magnetic condenser lens. When the beam passes through a sample whose magnified image is needed, the beam carries the image of the sample. With the help of magnetic objective lens and magnetic projectile lens, the magnified image is obtained on the fluorescent screen. Next, we will see the comparison for light microscope and electron microscope. In light microscope, the electromagnetic spectrum ranges, that is visible light, 390 nanometer to 760 nanometer. In electron microscope, it is approximately 4 nanometer, that is electrons. For the radiation source, tungsten or quartz halogen lamp in light microscope. In electron microscope, it is high voltage, that is 50 kilovolt tungsten filament. In light microscope, the lenses are glass. In electron microscope, it is of magnets. In light microscope, the focus is the lens is movable. In electron microscope, it is rigidly fixed, adjust lens currents. For focusing screen, in light microscope, it is of human eye. In electron microscope, it is fluorescent screen, photographic film. In light microscope, the stains is water-soluble dyes. In electron microscope, it is heavy metals. The support of light microscope is glass slide. In electron microscope, it is copper grid. Next, the most important topic is X-rays. First, we will see the discovery. Wilhelm Röntgen in 1895 discovered that whenever fast-moving electrons fall on certain materials, a highly penetrating radiation is emitted. Since their origin was not known at that time, they were called as X-rays. Now we will see How X-rays are produced. X-rays are produced in an X-ray tube, and this figure shows a schematic diagram of an X-ray tube. From the figure, we can see the X-ray tube that is consists of an evacuated glass tube to allow the electrons strike the target without collision with gas molecules, and a heated filament as a cathode is made from the material of lower ionization energy. A target, that is anode, is made from a heavy metal of high melting point such as tungsten and molybdenum. A cooling system that is used to prevent the target from melting. A high voltage source that is used to set the anode at a large positive potential compared to the filament. When a filament, that is cathode, which means negative, is heated by the current supplied to it, many electrons are emitted by thermionic emission. We know what is thermionic emission. These electrons are accelerated towards a target which is maintained at high positive voltage related to cathode. The high-speed electrons strike the target and rapidly decelerate on impact. Suddenly, the X-rays are emitted. X-rays emissions can be considered as a reverse of the photoelectric effect. In the photoelectric effect, electromagnetic radiation incident on a target cause the emission of electrons. But in an X-ray tube, electrons incident on a target cause the emission of electromagnetic radiation, that is X-rays. Next we'll see the characteristics of X-rays. We know that X-rays are electromagnetic waves of short wavelength ranging from 0.1 to 100 Armstrong. X-rays travels in a straight line with the velocity of light. The next is X-rays cannot be deflected by electric or magnetic fields. X-rays can be diffracted by the crystal lattice if the spacing between two consecutive planes of atoms approximately equal to its wavelength. The next is X-rays affect photographic film. X-rays can produce fluorescence and photoelectric emission. Next point is X-ray penetrate matter. Penetrating power is least in the material of high density. These are all the properties of X-rays. The next one is X-ray spectra. We know that X-rays are produced when fast-moving electrons strike the metal target. The intensity of the X-rays when plotted against its wavelength gives a curve is called the X-ray spectrum. Based on the X-ray production, this X-ray spectra consists of two types. One is a continuous spectra and second one is a characteristic spectra, that is line spectra. In the first graph, we'll see the X-ray spectra of tungsten at various accelerating potential. In the second graph, the X-ray spectra of tungsten and molybdenum at a particular accelerating voltage, which means for a given accelerating voltage, the lower limit of the wavelength of continuous X-ray spectra is same for all targets. This minimum wavelength is called cutoff wavelength. In the second graph, the intensity of X-rays is significantly increased at certain wavelength, that is characteristics X-ray spectra for molybdenum. The first part is continuous X-ray spectra. What is continuous X-ray spectra? When a high-speed electrons which bombarded the target undergo a rapid deceleration. This is breaking. As the electrons suddenly come to rest in the target, a part or all of their kinetic energies are converted into energy of electromagnetic radiation, immediately called Bremsstrahlung or breaking radiation. According to X-ray spectra, the continuous spectrum has a minimum wavelength. In this figure, a fast-moving electrons which bombarded the target which undergoes a rapid deceleration and it is breaking where the X-rays are generated. The existence of the minimum wavelength is due to the emission of the most energetic photon where the kinetic energy of an electron accelerated through the X-ray tube is completely converted into the photon energy. This happens when the electron colliding with the target is decelerated and stopped in a single collision. If the electron is accelerated through a voltage V, the kinetic energy of the electron is equal to the electric potential energy. Therefore, kinetic energy K equal to electron volt EV. When the kinetic energy of the electron is completely converted into the photon energy. Thus, the minimum wavelength lambda naught of the X-rays is EV equal to E. Therefore, EV equal to hc by lambda naught. We note lambda naught is a minimum wavelength. By doing cross multiplication, we get that lambda naught equal to hc by EV. From this equation, the minimum wavelength depends on the applied voltage across the X-ray tube and independent of the target material, where lambda naught is the cutoff wavelength, that is minimum wavelength. By substituting the known values of the above equation, that is h is a Planck constant, c is the velocity of light, and E is a electronic charge, then the lambda naught equation becomes 12,400 by V into Armstrong. This relation given by equation known as the Duane-Hunt formula. And the second part of X-ray spectra is characteristics X-ray spectra. X-ray spectra show some narrow peaks at some well-defined wavelengths when the target is hit by fast electrons. The line spectrum showing these peaks is called characteristics X-ray spectrum. This X-ray spectrum is due to the electronic transition within the atoms. The characteristics lines are the result of electrons transitions within the atoms of the target material due to the production of characteristics X-rays. This figure shows the X-ray spectrum is due to the electronic transition within the atoms. The first is K series, that is K lines. It is defined as the line spectra produced due to electron transition from outer shell to K shell vacancy. The first is K alpha line. K alpha line means electron transition from L shell to K shell, that is n equal to 2 to n equal to 1. The next line is K beta line. K beta line is nothing but electron transition from M shell to K shell vacancy, that is n equal to 3 to n equal to 1. And next is K gamma line, which means electron transition from N shell to K shell vacancy, that is n equal to 4 to n equal to 1. The next series is L series. L line series is defined as the line spectra produced due to electron transition from outer shell to L shell vacancy. In this, L alpha line is nothing but electron transition from M shell to L shell, that is n equal to 2 to n equal to 2. And the next is L beta line, which means electron transition from N shell to L shell, that is n equal to 4 to n equal to 3. And the next line is L gamma line, which means electron transition from O shell to L shell vacancy, which means n equal to 5 to n equal to 2. These line spectra can be illustrated by using the energy level diagram as shown in the figure. The last topic is applications of X-rays. X-rays are widely used in many fields. The first is medicine. In medicine, X-rays are used to diagnose illness and for treatment. For soft X-rays of low penetrating power are used for X-rays photography. X-ray penetrate easily soft tissues such as the flesh, whereas the bones which are high density and absorb more X-rays. Hence the image of the bones on the photographic plate is less exposed compared to that of the soft tissues. In industry, X-rays are used to check for flaws in welded joints, motor tires, tennis balls, and wood. At the custom post, they are used for detection of contraband goods. In scientific research, X-ray diffraction is an important tool to study the structure of the crystalline materials, that is, the arrangement of atoms and molecules in crystal. The example is Bragg's law. Now we just recollect what are the topics we had seen. De Broglie wavelength of electron and DAVISSON and GERMER experiment, electron microscope, X-rays protection, properties, types, and applications of X-rays. Thank you.